Hello everyone. Am I audible? Hello, am I audible? Yes. Okay. So the last class we started with autoencoders, and we sort of pointed out what are the things autoencoder do, like representation learning, denoising, compressing, and all these things. Then we specified the loss of autoencoder, and then we also specified the application domain of autoencoder. And yes. So last class we completed sort of autoencoders. So this week we'll start with the coding part. Week 4. Three. So so we'll start with the coding part. And so if you could go to the lecture number 12 Python file, you can run it with me. And so like before starting with coding, has anyone of you has any doubts or anything that can that need to be solved before? I guess till week 4 assignment as an answer has been released, so we can discuss till week 4. But this is a content of week 3, I guess. But yeah, anyone has any doubt that need to be clarified? Sumit and Chilakala Santi. Okay, so I'll start with the coding part. So I'll just explain these things, and as I'm assuming that you guys are getting it. And so if you don't get anything, so first thing I would suggest that whoever has joined the meeting to open, to go to the GitHub link that is there for this course. This is this link. I'll just share it in the chat. This is the link for code. And then I will I would request all of you to clone this. You can just go here and copy this and clone the repository. If you don't know how to clone, you can just go to the lecture 12 and download it directly. So here is a download button. It is there, or you can just copy file from here. You can download or copy. So I hope that everyone is aware how to install Jupyter and how to set up Python and all other packages. And if you don't have that knowledge, kindly refer to the earlier videos in the course to know about that. And if you have set up, so then we can start with the coding part. I'll try to increase the font size such that it will be visible clearly. Okay, I guess it is visible clearly. So first thing is that we will load the packages. Give me 1 second. So these are the packages, and that is there. Like you need to load these packages. So a common way to load these packages into your yeah, yeah, a common way to load your packages into your 1 minute. Mm. A common way to load your packages is to kind of first look into the so one command is import. So I guess like you are familiar with Python, but yeah, so if you're not familiar with Python, then this is the thing, like you need to import all these things initially. Like torch is a library for deep learning, and numpy is for doing matrix operations and all, and matplotlib is basically for plotting and all these things. So when you run the fast cell, all these packages will be loaded. And second is loading the MNIST data set. So this is the code for code that need to be written to load the MNIST data. So you just run it, and it will be downloaded, and it will be stored inside this folder, MNIST. Okay. So are you guys following, like Sumit and the other guy, Chilakala? So are you guys following with me by running the code, or you are just looking into the explanation? Okay, so till this cell number 2 is a code run. Like, is it running okay? So so then where so you can see, so mnist folder is created, and inside that mnist there is another mnist, and inside that mnist there is a raw folder is there. And so the data path is now mnist/raw. So these are some functions that are used to get the encoding and parse the bytes. You can just run it as it is. These are function you just have to use. You don't need to think about it more. Then read image file. To read the image file, this is the code. And to read the label files, these are the code. So once all these things are functions are done, then you can load these functions and kind of um, breed these images as train images, train labels, and test images and test labels. So I have a, so as we discussed earlier, uh, so as we discussed earlier, we discussed earlier. So, I'll just give you a brief overview about MNIST and how that works. Uh, so MNIST is a dataset for handwritten digits, like suppose say 7. So the number of pixel in this height is 28 and width is 28. And if you look into 28 plus 28, it will be 784. I guess 784, I guess. So this is the number of pixels, and it will have a, this is the image, and it will have a corresponding label as 7. Okay. Uh, okay. So these train images will have all the 7, 8, 9, 10 images, and these train labels will have the corresponding integer values. So if I run this, so all these things, all these train images and test images now will be loaded into these variables: train images, test images, and 10 labels and test labels. So now we can so this is a torch tensor. PyTorch is a library, and what is tensor? So tensor is something I can say. Suppose I have a like 2, 3, 1.5. So it's a 1D tensor. So tensor is a term used. So tensor is a generalized term. You must have learned that this is an array, okay, or list. But when I put a torch inside, torch dot tensor, so it's a like kind of it's a kind of tensor now, okay. So it's a tensor now. So this tensor will be it's a one-dimensional tensor, and this can be written as R1. Okay. So if a tensor is like 2, 3, 4, and 7, 8, 9, then it will be a 2D tensor, which will be equivalent to R square. Okay. And this, in general term, we call it as a matrix. Also, this also we call as a vector. But anything we can say as tensor. This is a tensor. This is a tensor. A three-dimensional tensor is also there, where we represent the RGB images: red, green, and blue. So it's a 3D tensor. But normal image like MNIST, it's a grayscale image. So it's a 2D tensor. Okay, so when we so we have a function called size inside PyTorch. So whenever you whenever you look into any tensor, you just put dot size in front of it. It will give you what is the size of the tensor that is there. So train images. So what we did is that we took this. So what we did is that we took this 2D tensor and make it into a 1D tensor. How? So we took this 28 plus 28 and sort of flatten it. After flattening it, we got a long vector or a 1D tensor, and this will be r to the power 1, and its size will be 784. Okay, and since we have loaded all the 60,000 images, the size of the tensor will be 60,000 cross 784. Similarly, for labels, it will be 60,000 cross 1. So we haven't described 1 here, but it is 60,000 cross 1. And similarly, for text of examples, we have 10,000 text examples, and we have 10,000 corresponding labels for that. Okay, so till now this is clear, I guess. So okay. Till now this is clear, right? So whenever I'm asking, just say yes or no in the chat if you don't want to open up. But if you do not say, I won't know. Based on different argument for train image is in coding part. Train image. Where is it? Train image. Different arguments for train image. So which line this, or is this one? So Sumit, you can, okay. So this is a read image file. Read image file is a function. Okay. So read image file is a function that is described here. So here you just have to give the path of the image. And then this function will do the work. It will go there and read the image, and that will try to convert that to a byte tensor. Then it will return you all these things. So you can just use it as it is. Like you can just assume that this is a function to read the image, and this is the path we are providing. So what is this path? So if you go data path, so we are joining the data path with this. Data path is this one, mnist/mnist/raw. So you go to mnist/mnist/raw. Then the train image path is train images ITX3 U byte, which is this one. Train images ITX3 U byte. So since it is in byte format, not in the correct like normal image format, we are reading it like this. We are reading it using byte tensor. Okay, is that clear? So these are just functions, just utilities to reading the image file. No science is going on there. Okay. So is it clear, Sumit? Like you can just use it as a reading file. Don't need to know everything. So then the next log is checking the availability of GPU. So in your laptop, the GPU is available, then you can try this. If it is not available, then you can use a normal CPU. Both is fine. So when I run this, it is saying the GPU is available. Okay. So then coming to defining the autoencoder. Okay. So last class we covered this one. If you haven't seen, you can just go back there and see how we described there. But I will just go through a little bit. Like autoencoder is kind of like this. Autoencoder is kind of like this, where we have an input layer, and okay, sorry, go here. So we have an input layer, and we have a hidden layer, and we have an output layer. The input is passed to the input layer, then that is passed to the hidden layer, which is we generate the Z. From Z we try to reconstruct the input X, and we optimize all these things. We optimize all these things such that the reconstructed image will look like the input image. So in PyTorch, I'll just let you know, Whenever you try to build any neural network or any deep neural network, so you have to write a class. So here we want to build the autoencoder. So we're writing autoencoder class. And for writing the neural network, we need to do this. We need to inherit this one, like nn.module. So after inheriting this, uh, we can do what we can do with that. So we'll initialize the autoencoder. So this is the parent class and this is a child class. So we have to write a super constructor. So in super, we'll just pass the class name and we'll just pass the blank. And after that, we'll define the network. Okay. So in network, the network is typically sequential. Sequential means all the layers, all the neurons of one layer is connected to all the layers of the next layer. So it is a linear kind of thing, and all the layers are connected to next layer, and one after another is block is added. So to do this, here our image size is 784. So we are passing 28 plus 28, which is 784, and the output is 100. So here it is 100. And from here, so this is the encoder part. For decoder, we will take the same 100 and try to output it as 28 plus 28, like this 100 28 plus 28. So this will be our network, and so this is the encoder and this is decoder. So then in the forward method, we'll define how the input will flow from the encoder to output decoder. So what it will do is that it is, so we'll just so in the forward function, we have the input x that we're getting. So we'll pass the input x to the encoder. Okay. So I'll just rewrite it so that it will be better. So we pass the input x to the encoder, and we got the z here, and then we'll pass the same z to the decoder. Then we'll get the same. Then we'll get the x hat or x dash, anything x and x dash, and we'll return the x hat. Okay, I just rewrote the variable name such that it will be easily understandable. So this is the setting. So did you get how a network is defined, and then how an input is getting like how we are passing the input uh, through the network? Did you get it? Like if you don't get it, like it will be very difficult for you to understand again the next lecture. I'll assume that you got it. So we are trying to print the autoencoder now. So you can see that the autoencoder is consisting of encoder and decoder. Encoder is a sequential network. The input is linear. It is connected from 784 to 100. And the decoder is linear, which is connected from 100 to 784. So, as we know that like for training anything, we sort of need a loss function. So what typically happens is that in neural network, you need to minimize something. So you need a goal. Why you are learning something? You need a goal, right? So here the goal is that my input image should be identical to the output image. So what we need the distance between the input image and the output image to be small. Or we can say that we want the L2 norm or the squared norm between the input image and the output image to be small. So the function and how to minimize, I already discussed that. For minimization we use gradient descent. So this is the like MSE loss, mean square error loss. So I am defining the criteria for optimization is MSE loss, and the optimizer itself is stochastic gradient descent. So stochastic gradient descent is a variant of gradient descent. So in neural network, so I'll just try to point out what are the things that you need to care when designing a neural network. First thing is the network architecture. First thing is the network architecture. You define the network architecture. Second thing is, uh, I'll define network architecture like the input layer, hidden layer, and output layer. It's a fairly good network architecture. Here the dimension is 728, 784. Here it is 100. Here it is 784, I think. Okay. And here we are passing X, getting Z, then getting X test. Okay. X test. Okay. This is a network architecture. The second step is flow of information or input. Okay. So it is so this is defined inside init function. Using nn dot sequential. Okay, so this is the this part. This part. So this is defined using different network. This can also be done using only one network also. So they're kind of doing two network and flowing information from one network to another. So this is the thing. Second is flow of information. So you need to define how the information is flowing. So you need to define that in Z equals to encoder X and X dash equals to decoder Z. So you just saying that the input will pass to the encoder will spill out Z, and that Z will be passed to decoder and will spill out X dash. Okay. So you define the flow of information. So now you have input X and the output X dash. Okay. In the third step, you need to define the loss. I mean, how you are trying to punish the network. So network initially it will have a random value. So this random value network will have random weights. And what you are doing is that you are taking this random weight, taking these random weights, and then you are kind of updating the random weights. Okay. And how you are trying to update? We are updating the weights in such a way that your end goal will be achieved. How your end goal will be achieved? So our end goal is that X should look similar to X dash, or you can say difference between X and X dash should be 0, or you can say the norm between X and X dash should be minimized. So when you get to a point where you know this something is to be minimized, this is your loss, or you can denote it as J. Okay. So this is a loss. and we are defining the loss here. It is typically defined using criterion. So the criterion is NN. NN is the module in PyTorch where all the neural network steps are there. MSE loss. You're defining this loss and you will apply this loss later. Okay. So MSE loss is mean square error loss. And to minimize this loss, you need a, so this is the loss and you know it, you need to minimize. Okay. So, but how do you minimize? Who will minimize? A minimizer will minimize, or an optimizer will minimize, or there should be a technique which should minimize. This is the optimizer. I think that's it. Loss, then optimize, or in this case, minimize. So you need a minimizer or optimizer. The best method is SGD. SGD, which is sto- stochastic gradient descent. Okay, so the SGD is stochastic gradient descent, and SGD. So stochastic gradient descent is a variant of gradient descent, and you are using this to minimize the loss. Okay, and you can use this stochastic gradient descent everywhere almost. So, so you define the criterion. So then comes the training autoencoder part. So how do you train a neural network? So here it is autoencoder, but you can train any neural network out of it. So what you are doing is that so how many times you have to train? You have to train it using so you can choose that. Okay, I need to train it for 30 times. You can redefine the iteration and everything. I will just do everything and show you. And then you are defining a batch size. So what batch size you are doing? So batch size means so when you're doing gradient descent, what you're doing is that you are finding gradient of any input or a batch of input at x. Then you are looking at the sign of gradient and you are sort of traveling the opposite direction. Since this is the minimum and this is the sign of gradient, by traveling in the opposite direction, you will eventually reach in the minimum point here. Okay, this was the thing that we discussed earlier. You can go and watch the videos again. Couldn't get it. Yeah, so this is the thing, and the first thing they're doing is that they're just iterating over the iterations. Like so iterating through the entire data set once is called epoch, one epoch. If you do it for like 30 times, it will be 30 epochs. Okay, and we're looking into the loss, what is the loss that is there. And then what we're doing is that then we are parsing the images. Okay, so we need to do 30 iterations, and in all 30 iterations I will go through all the images. Okay, then I will pass so then I'll do this 4 step. Okay, so okay, so this is the framework for any neural network. Then I will mention the training. For training, first you need to do first thing, forward pass. Second thing is calculate loss. Third thing is backward pass. Then fourth thing is update the weights and biases. Okay, so okay. Uh, so what you're doing here is that we are passing over the batches, which is clear. Then we are sort of so these all these three steps are like kind of inputs is your X. Okay. So all these three steps is just taking the input and putting it to device. Like if your input is in GPU and your network is in GPU, so all these things need to be in same device. So your network is to be in the GPU, and if you have a GPU, then you also have to put your inputs to your GPU. If you don't have a GPU, then you just have to write as it is. You don't need this step because by default it will be CPU. You need to set the device for tensors and networks. So this is the input. You are dividing it by 255 to need to kind of normalize that, and this is the input you are passing it to the device. Then this line optimizer dot zero grad. So when you are calculating gradient, so when you're doing backward pass, you have to find the gradient. Okay. Since you're doing the gradient and you don't want your previous gradient to be there and get add up, you just need to zero your gradients. This is the step zero grad. Okay. So here from here, the step starts here. So this is step one. Step one is this is the net neural net, and you are passing the net input to the net. So just net, then input, and then you're getting the outputs. Okay. So this is step one. Second thing is that you will calculate the loss. Step two, calculate loss. So this is the forward pass. Okay. And this is the loss calculation. Okay. So loss calculation, or I can say calculate loss. Calculate loss. So when you're calculating the loss, you're getting that. So criterion, you remember criterion is your MAC loss, mean square error loss. So this loss should be between X and X dash, right? Or in this case, X and output, right? So outputs and inputs. The criterion is between this. This is the loss you're getting. Then you need to back propagate that loss because you need their gradient, right? Step three is back propagation. So step three is backward pass or back propagation, what you're saying. And so this is done by loss dot backward. So this is so simple, like you can just write any neural network now. Step four is updating the weights. So optimizer, so updating weights and white biases. Optimizer dot step. When you write this down, it will be like it will take a step, like it will update the weights. So how the weights will be updated? I also like specified earlier. Weight new weight equal to weight t plus one t plus one equals to weight t plus weight t minus alpha into gradient of x plus x dash. So all these things are, so this is actually lambda into, okay. So lambda is the learning rate. So I have already specified the learning rate, like when you're taking a step, here, so you're concerned about what is the amount of step that you are taking. It shouldn't be like too large. If it's too large, you will skip the minimum. So we're just minimizing the step to some extent. So this is the lambda you are doing. So all these are discussed in lecture 2 or 3, I believe. You can just go back there. But so the beauty of PyTorch is that all these things you don't need to worry about. You can just write this one, optimizer dot step. All these things will be done under the hood. Then we are keeping track of the losses, and at the iteration end, we are showing that okay, at this iteration, the mean square error is this one, and at this iteration, the mean square error is this one. And after all these things are done, we are printing that training is finished. So then I'll just try to train it now. So once this is do start training, so you can just uh, ask me any doubt if you have. So you can see iteration 1, 2, 3, 4, 9, 10. So mean square error, as we are minimizing the mean square error between x and x dash, it should be decreasing. See 0 0.81, 0 0.05, 0 0.04, 0 0.03, 0 0.02, then decreasing 0 0.01. So the training has finished. So do you have any doubt regarding this, like how the training has happened? If you have any doubt, you can just ask me now. Hello. So do you guys anyone have any doubts as of now? Anything regarding the, so Sumit, you are running the code. Uh, so were you able to train the network, the autoencoder? Okay, no response. So I would suggest, as I would assume that you have run. So then I'll go to the testing part. So in the testing, what we are doing is that now our autoencoder is trained, and these weights are now we have learned and it is fixed. So here, so then what we need to do is just do this forward pass only in the testing. In testing, we just need to do forward pass only. I will run the code here. The net is there, and okay, so test. So this is the part. So this is the test image where that we are getting from the test images, and we're passing this test image to the net or the network, and we're getting the output images. This is the output image, and so these steps are like modifying the output image such that we can visualize it. And these are the steps to visualize the. There's a code for to visualize the output image. So this is for the original image, and this is for the reconstructed image. Okay. So when I run this, I'm getting this 2 and the reconstructed image. So as you can see that the 2 here is getting reconstructed, not perfectly, but somewhat better, I can say. Like we still can look at it and say this is 2. Okay. Then we will try to visualize the weights that we have learned through this. And see, so this is the initial weight. Like initial weight is this, like the weights that we defined, the random weights, and this is the after training. You can see that after training the weights are pretty much um, synchronized and pretty much arranged, and update is this. So this is the weight update, like what is the changes this weight went through to reach here. So this is just a visualization, you don't need to worry about it. The main thing is that you put it 2 and you get back at 2, which just looks similar to 2. So this code has not done, but I will try to improve this too. Okay. The first thing we can do is that we can deepen the network. To deep the network, I can just add another layer and enter linear, where the input will be 100 and output will be say 64. Okay. In between, I can put a value. Similarly, I will also do this here. I can just put a value here and value and that linear 100 to sorry, sorry. That uh, linear. This is 64 to 100 and value and this 64 to 100, then 100 to 28 plus 28, then we're getting value. So if I just print this, you can see that the network now has changed. So the encoder is linear 784 to 100, then linear 100 to 64. The decoder is 64 to 100 and then 100 to 784. So if you look into the image, like the corresponding layers, it will be like this. So this will be like 784, then it will be 100, it will be 64, then 100, then 784. Get it? Like this. So, yeah. So this is the image, and then we just run everything else. We just change that one. Just try to run everything else, and we'll try to see did we get any improvement or not. So we did not get any improvement here, but we can keep on trying and trying and see what happens. Uh, hmm. You can put a sigmoid here and see. Sigmoid is another activation function, by the way. I do not think we're getting any improvement, but still we'll see. Yeah. So we get a, I guess we get a better 2. It is blurry, but it looks like a 2, and we don't have any gaps in between. Let me try with, let me remove this relu part and see what is happening. Invalid syntax. Okay. We're still getting the blurry one. We can try increasing the iteration to say 100. Wait. And yeah, now you can see it is a very clear 2. You can see, right? I guess everyone can see. So are you guys with me? Grace and Sumit Kaur. Kindly reply like if you have seen this miracle. Okay. So we can see that the 2 is now a lot better. So let's just redo like what we have done and see if it is due to the sigmoid that we changed, or is it due to the number of iteration that we increased. So let's just put back this red loop and just change the sigmoid to red loop. And let's just try to run it for 100 epochs now. Okay, we'll try the testing now. Okay, so you can see that clearly Relu is not doing good. So we'll just replace the I don't know why the initially it was Relu, but I guess the output should be between 0 and 1. So sigmoid is a very good activation function for that. Give me 1 minute. Okay. So then we'll test now. See, now we're getting clear 2. Okay. And you can say that this is the better 2 than that we got earlier. So we'll do the weight visualization now. Okay. You can see the weights, but there is nothing to see. And this is the weight. Before going to the next part, removing the decoder and classifier, we'll try to take a short 5-minute break. So if you want to go outside, you can go and come. Since it is a 2-hour class, I guess a short break is needed. We'll resume at 5:15 again. Bye. Hello. Am I audible now? Hello. Okay. So, so what you can do is that, so remember we discussed earlier that autoencoder is also used for representation learning. So if you look into this, the concept of representation learning. So here is the input 7, input image say 7, and we're sort of learning a representation of this 7. Okay. And the dimension is 784 here, and it will be much more smaller than 784, let's say 100. Okay. Or in our case, let's say 64. Okay. And we are sort of learning the 64 dimensional representation of 7, such that all the information that is there in the 7, that should be there in the 64 dimensional vector, as well as if we use this for classification, it should be giving us good accuracy. So for example, so what is the advantage of it? The advantage is that instead of passing 7, now we can pass this 64 dimensional vector, and also we can store this 64 dimensional vector for our future use. Okay. So this will reduce the storage cost, as well as the computational overhead that is going to there, that was there in the original image 7. Okay. So what we are doing is that, so this was the autoencoder, right? So this was the input 7, and this was the input layer, and the input layer was, let's say, 784 dimension, and we are passing it to a 100 dimensional vector, and this 100 dimensional vector was again get passed to a 64 dimensional z vector, and this thing again was reconstructed back to a 100 dimensional vector, and again this was reconstructed back to a 784 dimensional vector. Okay. So just to recall, this was the case. This was the network output that was there. This one here. Okay. Now what I can so what I need is that what I need is that I need the representation, right? So I need this one. Okay. To get this one, what we will do is that we'll just discard all these things. We'll discard all these things. We don't need these things now. Now we have got the representation Z, and this we can process further. So our task is now to pass this Z to a classifier. Which will classify the digit 10-dimensional vector. This will classify the digit as 0 to 9. Okay. So is this thing clear? Like, instead of passing the 7 now, we are passing this representation of 7. So it's basically a long network like this, but half of the network is now trained and can now represent the representation of the input set. So is this thing clear? Then I'll go to the code, how it is getting implemented. Okay. Okay. So now you can see that so coming back to the code, we can see that so this thing is done. Yeah, classifier with encoder word visualization. So this we have done. Classifier word visualization. Where is this classifier defined? Here, the remove decoder and add classifier layer. So we are sort of removing this decoder and we're adding a classification layer. So this is like nn.sequential star list, then net.children up to -1. So we are taking all the children excluding the last layer. But so excluding the last layer. So we are sort of listing the children and we are taking the last all the things till last layer. If you remember, our initial network was like this, right? So if I remove this layer, my last layer will be Z. But now my network is looking like this. I need to remove the last two layers, not just last layer. To getting to the latent layer Z, we need to remove the last two layers. Hence, the code here I need to change here. It will be -2, not -1. We just need to delete the last two layers, and we'll get the new classifier. And this new classifier will be. Then we'll add another module, which will take this. So now, earlier the middle dimension was 100. Okay, so that's why we are adding 100 to 10 dimensional vector network. Since the middle dimension is now 64, we'll change this one to 64. Okay, did you get it? The linear, then we're adding a linear layer, and then we're printing the internet. So printing the neural net. So I'll just run it and show you. See, the classifier is now sequential, and okay, so you're printing the net, right? Okay, so the classifier is everything that is there in the encoder. Okay, but everything that is there till encoder, and then the next two layers. Then we'll define the optimizer similarly. So if you remember, the criterion or the loss function for reconstruction was MSC. Okay, so now we are doing classification. We need to go through this 4 steps again. So first we need to network architecture. The network architecture is defined here. Like we just removing this last two layer and adding another linear layer. So the resultant network will be, I'll just draw it here. It will be 7. This is X. So this is 784. It is 100. 64. Then we're adding 10. 10. Okay. So this is the thing. So this is the network architecture. The network architecture is not defined. When you pass all these things, you'll get a corresponding Y. Okay. So let me do. So yeah. So step number 1 is done now. Okay. So step number one is to define the network. We define the network by removing the decoder and adding another 10 neuron wala layer. The second thing is flow of information input. So how to define that? We have to define that using a forward function, right? So Okay, so they haven't. Okay, so since we're adding another module to in the front, so it will come along as a forward pass. So we don't need to worry about that. And forward is just like it is self-defined in this n dot module. In this n dot module. So since you are like adapting from encoder, we don't need to worry about the forward function because it is already defined for encoder. Okay. The third thing is specifying the loss. So loss here is the loss that was there in the initial classification was sorry, initial reconstruction was. So okay, so this was step one. Step two is done. Step three is specifying the loss. The loss was earlier it was x minus x dash L2 norm, right? But now we have a y. We cannot apply this. We have a y. So what we need to do? We have to do a NLL loss. It is negative log likelihood. Okay. The negative log likelihood is the NLL loss, which is minus y into log y summation. Something like this. So you can just look into it. But the thing is that it has a mathematical formulation. The thing is that it is a negative log likelihood. It will punish if a wrong prediction is made. So the work of this loss is that we need to minimize the wrong predictions. So suppose the image is 7, and if the y value is 8, it should punish that. Like it should minimize this. It should minimize wrong predictions, or you can say it is maximizing the right predictions. So it should maximize 7 as corresponding 7. So it should minimize the wrong predictions. So in this way, we can say that it's a valid loss function. Okay. I define the NL loss. Optimizer is same, like you can use gradient descent everywhere. So I am doing this. Then I am training the classifier. Okay. So let's just train the classifier. There is error 1784, 64 and 10. Okay. Let me do this. Let me put my autoencoder back as it is, because this code was written keeping in mind that yeah, this code was written keeping in mind that it will work for the above architecture. Since I have changed it, I guess I shouldn't be like modifying it much. It should be like this: 784, 100 RLU, then linear 100, 784 sigmoid. So this should work, I guess. Let me train it again. Training is finished. Testing is fine. It looks fine. Here need to be 100. This also looks fine. Minus 2, what will happen? Okay, it's happening. Okay, I see. I shouldn't be like, I should run it once, because once it is running, so then if I run it again, so it is kind of messing with the variable net, because net is defined twice. So inside that, so it is so this net, once I run this, so this net will the new classifier. If I'm running it again, it is just thinking that this net is this net. So it is creating problem, but I'll just run it once. Yes, it will be better. So let's just wait till it run. Yeah, now you can see that the classifier is 784, 100, 110. So I'll just redo this architecture. Okay. Initially we have this 7. It is 28 plus 28. We are flattening it and putting it inside a 784 dimensional vector. Then it is going to a 64. Sorry, going to 100. Then it is going to a 10 dimensional. Okay. You can clearly see this here. 784, 100, 100, 10. So this is the same 100. Okay. So then we'll define the optimizer, and similarly we'll train the classifier. So classifier, what is the steps? So I will just rename it. Up. Yeah, we'll just rename it like we did earlier. So till this point is input, like I'm just kind of putting all the input to the same device, and we're kind of putting all the labels to the same device. It is like normalizing the input. Here our step 0. Making the gradients of the network as 0. Since we don't require the prior gradients in the network, we need to make it 0. Second is step 1, which is forward pass. Forward pass is putting the input and getting the outputs. Second is step 2 is calculating the losses between the outputs and the labels. Step 3 is back propagation. Step 4 is updating weights. Then we're keeping track of loss of this thing. Let's just train the network. You can see the loss is decreasing and the testing accuracy is increasing one after another, and we reached at 92% accuracy. Okay. Then we are trying to visualize the weights now. See, so this is the weight it was earlier, but now since we are training it again for classifier, the weights have changed. Then we're trying to visualize the classifier's weight. So this was the initial weights. It was random. Then is the trained weights. It doesn't seem random, but yeah. Okay. So and also this is the updated weights. Okay. So this is the thing. So we'll try to increase this accuracy because we know that. So actually, MNIST can give you around 100% accuracy. So let's just so with this setting, let's just increase the iteration first and see if it is giving me any good accuracy. Hmm. And say that we reached till 96.4. I mean 96 to 97%. Let's just try to make it like one last time, make it 200 and see if it is giving me any better accuracy. Okay, so it is increasing now. So we can see that the accuracy has increased to 97.36. If you visualize the weight, I guess we won't see any significant change in the weights. But yeah, we can say that the weights are like now uniform around all these things. Okay. From a performance point of view, number of iterations should be small. No, the number of iteration is like you are training the network. So during training, you can try number of iteration. If it is attaining good accuracy in smaller number of iteration, then it is good. But if the accuracy is good and you're doing in a lot of iteration, then it is fine. It is okay to like I mean increase the number of iteration given that you are getting good results. So that much pain we can take, I guess. I guess we have completed this lecture number 12 code. Then we can move to the lecture number 13 code, where I guess it is for the fashion MNIST dataset. So before proceeding with this notebook, I would like to say that it is very similar to the one we discussed now. The thing is that fashion MNIST, the image instead of normal digit, it will now be any cloth, like it can be any shoe or it can be anything like any say pant, okay, or it can be anything like such as a vest. Okay, this is the only difference. So what is the point of difficulty now? What are the things it brings with it? First thing is that the dimension will be same, like it will be 28 cross 28 only. But the complexity of pattern that we saw in this image, it's much more smaller than here. Okay, because here it is real world images, but it was just digits. Real world image, like Sue will have like different pattern with and it will be very different than this pant, and this pant will be very different than this shirt. But if you see digits, so it is not so similar. If you see digits, 9 is somewhat related, like somewhat similar to 7, right? It just this bar different, or I can say this is also similar to 4, but this line difference. Okay, or this 4, only this line is different. Right? If you cut this and add this, it will be 7. So all these digits are very near to each other, but here you cannot like convert a suit to a panned very easily, right? So this is a complex pattern than the original digit images. So there is a difference. So let's see how this when you load the packages and run, how it is running. The first thing is that we'll load the packages. Okay, let me change the kernel. Then loading the data set, it will download. Data is downloaded, and I guess it was here, feminist or fashion feminist. The data path is this, and these are the same function that we used for parsing the byte, reading the images, and reading the label file. I guess it will throw error. Yes, because they didn't specify the path correctly. Here I will correct this. Feminist, then fashion feminist, then raw is there. I guess it will run fine now. Okay, it is running good. Like we can see the output in some time. Yeah. So you can see the sizes. The sizes are same, like I told that 784, 60,000, 10,000, 784. Checking the availability of GPU. GPU is available. Now, see, earlier in lecture 12, they used a autoencoder of this size. 784, 100, 100, 784. Since we're now capturing a very complex pattern than earlier, it is 784, 100, 100, 100, then again 100, 100, the opposite, the 100, 784. Okay. So and this part is similar, like we're passing the X to the encoder, we're getting the X, I mean the Z, you can write it as Z. Then we're again passing the Z to the decoder, getting the X hat, returning the X hat. Okay. So yes, so just print the net. In the net you saw that 784, 100, 100, 100. 100, 784. Okay. Then again, the same thing, the same optimizer is used, like the MSE loss, the stochastic gradient descent, and we're training the autoencoder now. I am sure that like it will again come as like a scattered part because they use ReLU here. We'll try with sigmoid and see how it is getting trained. The training is finished. Now I'll try to visualize. See, this is a Lee T set or full set. It is coming as black and white patches. What we'll try to do is that we'll try to just convert this ReLU to sigmoid. ReLU is that it will, if it is less than 0, it will make it as 0. If it is more than 0, it will keep it as it is. Since these pixels are less than 0, it is just making it them as 0. So that's why we're getting this black patches, which shouldn't be happening, right? So that's why when you do sigmoid, if it is, even if it is less than 0, it will try to map it to a 0 to 1 value, so that you can so that you can always get a value between 0 and 1. Since we are normalizing this input and our input is between 0 and 1, you will get a valid color or valid shade of white. In 0 it is completely dark, in 255 it is completely white. In between you'll get a shade, it will be gray, something grayish. Okay, so let's just run it again. I'll train the autoencoder. I hope it will be better now, but let's see. Yeah, we got a somewhat better representation of the this set. Let's try to do a more number of iteration to see if it is doing any better. Then let's try 200. The training is done. Now you can see it. Yes. Yeah, we see some sort of leaves trying to appear here. We'll see the, we can just stay with it and see. They're the weights that is there. Give me 1 second. So, So they are the weights. Okay, so this is similar to the one we did last time. So we're removing the encoder, decoder, and adding the classification layer. Then we're defining a optimizer, same as NPTEL loss and LCD. We're trying to train the classifier, and we'll see what is the accuracy, peak accuracy that we get. Let's just try with 100 iterations. Should be touching 90, I guess. Then it will be good. Okay, we're getting 88. I guess that is fine. We'll just visualize the encoder weight and visualize the classifier weight, which is fine. But I guess we can go till 90. So this notebook was pretty straightforward. It was similar to same notebook. I guess I spent pretty much time uh, um, by doing explain the notebook number 12. I guess notebook number 13 will follow. It is a notebook number 13B, which is again, I guess. So what it is doing? Yeah, so it is just a normal autoencoder, I guess. Again, the same thing. Testing autoencoder performance, then we're adding more layers, then removing and training the classifier. It's a task that you just go and run. We'll come to the notebook number 14, and this will be the last notebook, I guess, for today's session. So all IDB is acute lymphoblastic leukemia image dataset for image processing. So here the steps will be similar, but now the autoencoder has to be very, very, very complex. Why? Because this leukemia dataset is a color image. So as we know, color, there are 3 channels: red, green, and blue. And this dataset size is 32 cross 32. So 32 cross 32 cross 3 is only the total number of neuron in the input layer. And everything else will be same, like we're putting it to 100, then 100, then again 100, and then from 100 we're reconstructing back 32 plus 3. And then we're again defining the optimizer, training the autoencoder, then we're visualizing the weights and everything, training the classifier then, and visualizing the classifier weights and all. So I'll just run it once and see what is happening. I guess uh, it will be running within 5 minutes. Let me try run. Loading the data, file not found. Okay, so I guess for this I need to download this data earlier, but I haven't downloaded earlier. So I guess it is not a good idea to proceed with this. Okay, so this is again another data set. Lecture 17A. Okay, stack autoencoders, and stack autoencoders will cover next class. But I guess this data set, okay, drive 14 data set, right? Should be there. I don't know why. Okay, data set for image processing. I guess I need to download this data set first, then run this. So what you can do is that you can download this data set and run this notebook, the notebook 13B and 14, and let me know the results that you got in the discussion section. This is the all IDB data set. I guess you need to download it from here, this page. Let's see, download Yeah, you can just go to this page and download the dataset, and I guess you have to, I guess, apply for it. Application name, university, department, all these things, email, fax, phone number. Then only they will give you the dataset, I guess. Otherwise, I guess it is not publicly available. So yeah, so you can download the dataset and try to run and put it inside this folder, all IDB2, and then run the code. I will keep this downloaded next time, and I will try to run this code again in front of you in the next. And yeah, so I guess this is pretty much it. We covered everything, almost everything in the code of autoencoder. And since week 4 is also autoencoder, this will help you a lot. Like it, I will just I'll just tell you what is the modification to the code. I'll not go through the details. Okay, please share the recording of this session. So all these recordings will be added to this channel. So I'll just reshare the channel again for you to see. This is the channel. This is channel, you can go and subscribe there, and so that you can get the notification whenever this video will be updated. So I will try to update it within half an hour, because it takes half an hour to update. So till week 3, everything is uploaded. I will upload the week 4 content today. So yeah. Anything else that I need to do? Thank you. Thank you. I guess it's 6 p.m. now. We can end the session for today, and we'll meet next week. Bye. Grace. Grace, I guess you are a new joining for the first time. You can subscribe to the channel that I said earlier. Then you can get all the videos that is there from week 1. We covered everything using, all the deep learning concept, ML basics, and gradient descent. Okay. Thank you. I'm stopping the screen share and ending the meeting.